the steam turbines and gas turbines is that in steam turbines you need to have a very elaborate setup which consists of your steam generators, steam nozzles, and lastly your steam turbines. And that is quite an extensive setup because it requires a huge area to set up the whole plant, and it is more suitable for generating power of a large quantity in larger scale. Okay, in most of the cases more than 1000 megawatts. uh, the the reason where this gas turbines comes into the picture is that the area required to set up a gas turbine plant is fairly small. You don't really require a huge boiler to start producing steam which will power your turbines. In gas turbines, the setup is fairly small. The upfront costs are fairly small as compared to your steam generators. So, before we proceed, I'll just brief you regarding the course objectives. The course objectives are to study the boilers, boiler mountings, and accessories. Second one is to study the utilization of thermal and hydraulic energy. And third one is to study the gas turbines and its applications. Okay. Now, I believe you all have you all have been taught by Dhaval sir the water turbines, right?
Yes, sir.
Yes, sir.
Yeah. So even for the water turbines, the investment cost is quite huge. The area required, the land area required to set up a hydropower plant is also quite huge. Now, the gas turbines have the advantage that they require very less area. Uh, they are fairly portable. Okay, and they can easily be used as a standalone or a backup power plant. So we'll just briefly go through the types of power plants that are there worldwide. You have your nuclear plants, you have wind farms, you have wave energy harnessing farms, you have geothermal energy farms, tidal energy farms, you have biomass plants, hydrogen plants, hydroelectric power plants, solar power plants, oil based plants wherein oil is used as your heat giving or heat producing medium, coal-fired power plants, which are more extensively used in India, and of course you have the solar farms. Okay. So, out of the steam turbines, steam power plants that we have seen, oil and coal was the preferred choice. Coal was rather the more preferred choice because it is fairly easily available in India and it is fairly cheaper. Okay. uh, but for example in gas turbines, oil and natural gas are the preferred fuel. Okay, so I just got this data online. The total power stations that are there in terms of their subcategories, you can see that coal is around 57%, uh, and you have got gas turbine power plants which account for around 7%. Okay, and nuclear is around 2%. Other renewable energy sources, which include solar, is around 20.5%. Hydro power plants are around 13.2%. Okay, so these are a few examples of the gas turbine plants in and around our state of Maharashtra. We have Dabhol power plant, which is situated in Ratnagiri, that is generating around 2200 megawatts. Now, this was installed fairly long before in 1970s. Uh, this initially used to generate around 700 megawatts, This was initially running with naphtha as fuel. Okay, and then they extended the plant, and now it is capable of running on liquid natural gas, that is LNG, and the total capacity is around 2160 megawatts. The second example is your gas turbine power plant in Uran, which is it is assembled and operated by Mahagenco. It accounts for around 672 megawatts. Then we have Varodra gas plant in Gujarat, which produces 310 megawatts. We also have a small gas turbine power plant operated by Tata Power in Trombay, which is able to produce around 180 megawatts, which acts as a feeder power plant to the existing coal-fired power plant operated by Tata Power. So we'll see how a gas turbine power plant is. What is the basic layout? What are the different components of a gas turbine power plant? So gas turbine power plants basically work on the cycle known as a Breton cycle, or it is also called as a Joule cycle. Okay, the main components of a gas turbine power plant are compressor, uh, a combustion chamber, a turbine, and or heat exchanger, depending on the type of gas turbine power plant. It basically works on liquid and gaseous fuel. Okay, so this is how the layout of your gas turbine power plant is. First, you have an air compressor which is going to compress the air. Okay, and then that compressed air is sent to the combustion chamber. Okay, in the combustion chamber, air is mixed with the fuel where it is ignited, and there is a sudden pressure rise in the combustion chamber. The products of combustion are at a very high temperature and pressure, and then they are sent to the gas turbine. So here they'll get expanded. The expansion will cause the transfer of momentum into the turbine shaft, and that shaft, via means of uh, gear gear train, will be sent to the uh, generator where your AC power is generated, and then the exhaust emissions are uh, allowed to move out of the gas turbine. Okay, so this is how a gas turbine power plant layout looks like. Uh, Depending on the type of fuel, if you have an oil or liquid fuel, then you will have an oil storage tank nearby the uh, gas turbine power plant, where that oil is directly fed into the combustion chamber. If it is a natural gas or a gas fired turbine plant, then there will be a pipeline from where the pressurized natural gas is going to be entering the combustion chamber. Okay, here you have the air intake, you have your compressor which is going to compress this air, and both these air and the fuel are going to get mixed in the combustion chamber. They are going to get ignited, and that high pressure, high temperature products of combustion are sent to the turbine where they'll expand, they'll rotate the turbine, and they'll rotate the generator shaft connected to the turbine shaft, and hence you get your AC power. Now, this whole setup, if you just expand it, it is going to look somewhat like this. Now, can you tell me what what is it looking like? Have you seen this somewhere?
It is a turbofan engine, a plane engine.
Yes, very much correctly mentioned as by Neil. This is very much similar to your jet engine that you see. Okay, so in here in a gas turbine plant, your air is going to move in an axial direction. Okay, here you can see your air and then later on the products of combustion are going to move in an axial direction through the through the compressor as well as the turbine section. Okay, so we can classify the gas turbine uh, power plant in terms of their uses. It can be used in an aircraft in a jet or turboprop engine. It can be used in a locomotive engines, and it has got very limited or negligible applications now at this current time in marine or transport. But it is more prominently used in the stationary power generation units. Okay, is more commonly used in this stationary power generation units. So this can work as a peak load uh, power plant, depending on the location where that plant is. If it is not possible to set up any other large capacity plant, or if there is no requirement of such large capacity power, then it can act as a peak load power generation unit, or it can be used in a large scale industry as a backup power. Okay, or more commonly it is used to cater to the base load. Okay, uh, we can also classify according to the cycle. We can have open cycle gas turbine power plant, which is more commonly used one. Okay, we can have a closed cycle. This is not very common. We'll come to the details why the open cycle is more common. And you can also classify according to the arrangements. You can have a simple gas turbine power plant, single shaft, intercooled, reheat, regenerative, and combination of these. So as we have discussed, we can have constant pressure, open cycle, closed cycle, constant volume, uh, combustion chambers for gas turbine. The most common type is a constant pressure open cycle. Okay, so this is a closed cycle gas turbine power plant. Now in this case, as the name suggests, you will have the same working fluid which is passing through all the equipments. Okay, this means that uh, you cannot actually cause combustion in the combustion chamber. Okay, because if you cause combustion in the combustion chamber, then your working medium is exhausted. Okay, the oxygen is going to get exhausted over a period of time, and then your working medium will not be able to sustain the cycle. So here the heat is supplied via heat exchanger by indirect method. Okay, there is going to be a heat exchanger, and in this through this there will be an external heating medium. Okay, so let's say we are having air as the working medium. So air is going to get compressed in this compressor, and in the heat exchanger over here we can have oil burners or gas burners which are going to supply the heat to the air but indirectly. Okay, and then that high pressure high temperature air is sent to the gas turbine, where it is going to get expanded and this is going to rotate the turbine shaft. Other thing to note here is that both the shaft and the compressor are connected to the same shaft. Okay, so basically the gas turbine is going to drive the compressor, and the remaining power is going to get utilized in the electricity generator. Okay, and over here after the expansion, the exhaust working medium is sent to the heat rejection unit. It is again a heat exchanger which is going to ensure that uh, this working medium is cooled before it is sent to the compressor. Now the cooling of this working medium is equally important, because if it is not cooled to the initial condition, then over a period of time the core temperature of the plant will go on increasing, and after a certain time the temperature may be so high
सेकंड आउट करेल तर
that it can melt the turbine blades or the compressor blades. Okay, is the working of closed cycle gas turbine power plant clear to everyone?
Yes.
Yes, sir.
Yes. Okay, so currently we are having around 44 participants with us. Okay. So one thing you need to understand is that uh, gas turbine power plants cannot start on their own. Okay. Now, if you remember in your boilers, you just had to supply heat, okay, to the boiler, and then you could generate enough pressure steam, which can then be used to generate power. But here in your gas turbines, there should be some mechanism to start this cycle. Okay. Now, I think most of you all have traveled in aircrafts, right?
Yes.
Yes. So you must be knowing, you must have seen that the
That's
jet
it.
engine
एवढा
jet
टाइमपास केला
engine
त्याने
cannot start on its own. Okay. There is some external I mean there is an external pressurized air circuit which starts those compressor and turbine blades, and then it is started. Same thing applies over here as well. In a gas turbine power plant, there is it is essential to have an external starting mechanism to start this gas turbine power plant. So now we'll see what are the advantages of a closed cycle turbine power plant. Here you can see that the back pressure can be varied by a greater extent as the effect of pressure is not there. Okay, so obviously uh, because this is a closed cycle, you can select the pressure ratios you want. Okay.
हा 9 ना 7 प्लेयर
So
आणि 2 ह्याचे ऑल आउटचे
okay, so here you can select the pressures according to the most efficient operating points, and this turbine and compressors can be fairly smaller. Second point is that it avoids the erosion of turbine blades due to contamination. Okay, because it is the same working fluid that is passing through it, and it is itself is not participating in any combustion process. So it is not going to get contaminated by the exhaust gases and other things. So the turbine blades will not face the problems of contamination over a period of time. The third point is that there is no need of filtration of incoming air. Okay, if this was an open cycle, then this air would have been coming in the compressor from the atmosphere. So, if for an open cycle, we will definitely need an air filter to filter the air so that there is no dust particles that are entering the compressor. Okay. Next point is that as indirect heating is used, inferior oil or solid fuel can also be used. Okay, as I mentioned here, that your heat is being supplied by an external heating medium. So here you can easily use inferior grade of oil. For example, you can use heavy fractions of diesel, which are of course cheaper to procure. Okay, so here you can use your inferior quality oil or solid fuel also, but the process for solid fuel heating process is going to be extremely slow. Last point is you can use an alternative working medium like argon, CO2, helium, which has much more desirable properties. Okay, because since it is a closed system, there is no need or there is no restriction to use only air as a working medium. You can use argon or helium, which is having better thermodynamic properties as compared to your air. Next, we'll look at the disadvantages of a closed cycle gas turbine power plant. First point is that this system is dependent on external means, as a considerable quantity of cooling water is required. Okay, over here you see that you need to reject heat. Over here you need to reject heat in this heat exchanger so that you can cool down this uh, hot fluid that leaves the gas turbines. Okay, so here you need an additional cooling mechanisms which is going to add to your cost. Okay, and then again you will need to cool that water as well. Okay. So this system is dependent on external means for cooling. Second point is higher internal pressures involve complicated design of all the components and high quality materials are required. Naturally, as we were saying that uh, we can select the pressure ratios we want. So if you're actually going for a very high pressure ratio which gives you higher performance, then you'll need to select more stronger materials, more expensive materials. Okay. Next point is the response to load variation is very poor as compared to the open cycle power plant. This is the primary reason why your closed cycle gas turbine power plants are not used and open cycle power plants are preferred. The load variations, uh, the controlling the load variation is very poor in closed cycle gas turbine power plants. Last point is of course because you're using additional heat exchangers, so your space required to be much larger as there is indirect heating, and since there is indirect heating, you can the heat addition is going to take a lot of time as well as the heat rejection is going to take a lot of time. Next is the open cycle gas turbine power plant, which is the most commonly used type of gas turbine power plant. Here uh, most of the things are similar except that you need to add an air filter before the compressor so that no dust particles or dirt enters the compressor when the air is being compressed. Okay, and then you have your compressed air is then sent to the combustion chamber where the oil fuel is mixed or gaseous fuel is mixed and ignited, and the products of combustion are then sent to the gas turbine which rotate the turbine. That turbine is connected to the alternator or your electricity generator. That again is again connected to the starter motor. As I had mentioned before, you need starting mechanism for gas turbine power plants. So here your products of combustion are directly exhausted to the atmosphere. Okay, there is no need for additional heat exchanger to cool the products of combustion. Okay, because it is an open cycle, you can directly allow the products to exit into the atmosphere. Now we'll see what are the advantages of open cycle gas turbine power plants. Open cycle plants occupy less space as compared to closed cycle power plants because the use of the requirement of uh, heat exchangers is not there. Secondly, this combustion chamber can be much smaller because previously in closed cycle you had a heat exchanger over here. Because there is indirect heating in the closed cycle power plants, the area required for heat transfer is much larger. Okay, over here there is no such restriction since there is direct addition of heat. The combustion chamber is also smaller, and secondly, because there is direct heating, the you can easily vary the power output of the gas turbine power plants. So any hydrocarbon fuel can be used in the combustion chamber. Third point, negligible warm-up time. This is one of the major drawbacks. Major advantages. Negligible warm-up time is a major advantage for open cycle gas turbine power plant because the heat is directly added in the combustion chamber. The warm-up time is almost negligible. You can easily uh, come to the rated power within minutes of starting. Fourth point is the weight in kg per kilowatt developed is uh, okay. It should be more over here because the kilowatt per kg is more in case of open cycle power plants. Next point is fairly simple design of components. Sixth point is the response to load variation is better as I had mentioned, there is direct heating, so you can easily vary the power output almost instantly. The last point is the auxiliary components can be added, modified to improve the thermal efficiency. Okay, because uh, there is a it is not a closed cycle, so you can easily add any more components or any heat exchangers or regenerators, intercoolers if required, so that the tweaking or modification of this cycle is possible. Now we'll look at the disadvantages of open cycle gas turbine power plants. One of the major drawbacks is that the part load efficiency is poor. This is actually a drawback of gas turbines as a whole. The part load efficiency is always poor as compared to the steam powered. Next point is the chances of corrosion uh, in the turbine blades is higher. Okay, because the products of combustion are the ones that are passing through the turbine blades. There is the possibility of carbon deposition on the turbine blades as your products of combustion go through the stages of turbine blades. Third is that the filtration of incoming air in the compressor is essential, as I mentioned before. Efficiency of the plant is sensitive to air temperature, pressure, and humidity, because the air enters from the atmosphere. The air enters from the atmosphere over here. So any changes in temperature or humidity is going to affect the efficiency of the plant. So I hope you have understood both the open and closed cycle gas turbine power plants. Anyone is having any doubts?
No.
So next we'll proceed to the PV and TS diagrams that are there for your gas turbine power plants. First process 1 to 2. Okay, this is your isentropic compression that happens in your air compressor. Okay. Here you can see in the TS diagram, it is going to be a vertical line since it is constant entropy compression, isentropic compression. Okay. So 1 to 2 is isentropic compression. 2 to 3 is constant pressure heat addition process. Constant pressure heat addition. This is what takes place in the combustion chamber. It is a constant pressure heat addition process. 3 to 4 is isentropic expansion. This happens in the turbine. Isentropic expansion. This happens in the turbine. And 4 to 1, depending on the type of gas turbine power plant, this can be your constant pressure heat rejection. Just what we are discussing. Process 1 to 2 is isentropic compression, 2 to 3 is isobaric heat addition process, 3 to 4 is isentropic expansion, and 4 to 1, depending on it is an open cycle or closed cycle, can be your constant pressure heat rejection. If it is an open cycle, it is just a free expansion process. So of course, 1 to 2 dash is your actual compression, and 3 to 4 dash is your actual expansion in your compressor and turbines respectively. Okay. So next is the expression for efficiency of a simple Breton cycle. So we know that the compressor is driven by the turbine. So your turbine is going to first power the compressor, and the remaining power is going to be used to produce electricity. So work of compression is Cp T2 minus T1. Over here you can see T2 minus T1. Cp T2 minus T1 is your work of compression. This will be in kilojoule per kg. Work done in turbine is Cp T3 minus T4. 3 to 4 is your isentropic expansion. So Cp T3 minus T4. Heat supplied per kg of your fuel will be Cp of fuel into T3 minus T2. So thermal efficiency, it is defined as the output upon the input. The output over here is the net work done, okay, which is work done in the turbine minus work consumed in the compressor, divided by the heat supply, that is QS. So on solving, we get the thermal efficiency as 1 minus T4 minus T1 upon T3 minus T2. So again, if we write in terms of the pressure ratios, which is your P2 by P1, which is given as RP, we can get the efficiency of a simple gas turbine power plant as 1 minus 1 upon RP raised to gamma minus 1 by gamma. This is a fairly simple derivation. You can just refer to any book. You will get this derivation. So we know that the cycle efficiency depends on the pressure ratio according to this equation over here. Okay. So by increasing the pressure ratio, the efficiency should increase, which is what is visible in this graph. Now, this is what I was talking about. If you are using a more desirable working fluid, such as argon, whose gamma is 1.66, then your efficiency increases even further. Okay. So next we will discuss about the actual Breton cycle. Now over here, uh, you have your actual compression that takes place 1 to 2 dash. It is not isentropic, it is polytropic. So 1 to 2 dash is not going to be a straight vertical line in your TS diagram. It will be somewhat like this, and 2 to 3 dash will not be an isobaric heat addition process because there is always pressure drop as the fluid moves through any chamber. So in the combustion chamber, there is a pressure drop. So 2 dash to 3 dash is your actual heat addition process, and 3 dash to 4 dash is your actual expansion process. It is not isentropic, polytropic expansion process. So compressor and turbine efficiencies are going to change your isentropic compression characteristics. It is going to become now polytropic. And lastly, the pressure drops wherever applicable will change how your cycle looks. Okay, but from a syllabus point of view, we will not be analyzing the actual Breton cycle. We will only be analyzing the theoretical Breton cycle and some modifications that we can do on the